Electric current through a surface is the net flow of charge through it. Not all charges in motion contribute to an electric current. In an isolated conducting loop, no electric field can exist within it or on the surface. Even if conduction electrons are available, no net electric force acts on them, so there is no current. The figure shows a copper loop at electrostatic equilibrium. The electric field is zero at all points, and no current. A battery provides a potential difference. An electric field E is set up enabling the motion of electrons in the loop, thus an electric current I. Electrons from the conduction band in copper are free to move about and move in random directions. If we take a plane A prime in the copper conductor, the net transport of charge is zero, so there is no current in the conductor, even though there are electrons, negative charges in motion in the conductor. The figure shows a section of the copper loop with a plane A prime. No net charge transport across the A prime plane, that implies no current. The insertion of the battery in the loop creates a potential difference, and an electric field, E, that exerts a force on the free conduction electrons of the copper loop, thus establishing a current, I. A steady state is reached when the electron flow becomes constant. If we take a plane, A prime, in the copper conductor, where a current, I, is established, a charge dq passes through it in time dt. The current, I, is then defined as I equal to dq by dt, the total charge that passes through the plane, A prime, from 0 to t seconds as q, equal to, integration of dq, equal to, integration from 0 to t of I dt. The figure shows, a section of the copper loop with current, I, the same current, I, passes through A prime, B prime, and C prime under steady state, as the charge is conserved. For a current to flow, the loop or the path through which the charges travel, must be closed, there must be a potential difference, and the material through which the charges flow must be a conductor. Although semiconductors also allow the flow of current at certain conditions, the figure shows an electric circuit with a battery, a light bulb, a switch, and conducting wires, which satisfies the three conditions mentioned above, that is, 1. A closed path or loop from the positive to the negative terminal of the battery, 2. A potential difference provided by the battery, 3. Conducting wires. The SI unit for current is ampere, A, for coulomb, C, per second, S, C by S, ampere. A, is a base SI unit and electric current is a base quantity. 1 ampere is equal to 1 coulomb per second. 1 A equal to 1 C by S. Earlier 1 ampere was defined as the current which would produce a 2 × 10⁻⁷ Newton per meter force between two straight parallel conductors placed in a vacuum, 1 meter apart and having an infinite length and negligible cross-section. Now it is revised to the current equivalent to 10⁻⁹ elementary charges moving every 1.60217664 seconds, or 6.24150907 into 10⁻⁸ elementary charges moving in a second. Current is a scalar quantity. Since charge and time are scalars, current is not a vector, even though current is often represented with an arrow to indicate the motion of the charge, as shown in the figure. If the current I1 splits a junction, A, into two branches as I2 and I3, I1, equal to I2 plus I3, since the charge is conserved, the charge entering junction A should equal the charge leaving junction A. Bending or reorienting the wires does not invalidate the equation I1, equal to I2 plus I3. The figure below shows the same. The direction of the current is taken as the direction in which the positive charge carriers would move, even if the actual charge carriers responsible for the current are electrons or negative charge carriers that move in the opposite direction. The figure shows, the direction of current I is opposite to the direction of flow of electrons. The flow of electrons is from the negative terminal of the battery to the positive terminal, while the flow of current is taken from the positive terminal of the battery to the negative terminal. The magnitude of the current density vector, J, is current per unit area. Current density, J, is a vector. The direction of vector J is the same as the direction of velocity of moving charges if they are positive, or opposite if they are negative. If vector dA is the area vector of an element of a cross-section, the current through the element is vector J dot vector dA. The total current is then I, equal to integration of vector J dot vector dA. If the current is uniform and parallel to vector dA, I, equal to integration of J dA, equal to J integration of dA, equal to JA, where A is the total area of the surface, or J, equal to I by A. The SI unit of current density vector, J, is ampere per square meter. A by m square. The figure shows two wires, Wire 1 and wire 2 connected in series and connected to a circuit such that a current I flows through wire 1 and 2. If wire 1 and wire 2 have cross-sectional area, A1 and A2, and current densities J1 and J2 respectively, since A2 is less than A1, and the same current I flows through wire 1 and wire 2, J2 is greater than J1.